What if the most terrifying objects in the universe are also the key to understanding reality itself? Not stars, not galaxies, not even the Big Bang, but black holes, objects, so extreme that they tear apart our understanding of space, time, matter, and even information itself. For centuries, black holes were considered impossible. Even Einstein doubted nature would ever allow them to exist. Yet today, we have photographed them. We've heard them collide through ripples and spacetime, and now physicists believe these cosmic monsters may contain the final clues to one of the greatest scientific quests in history. A theory that unifies gravity and quantum mechanics. But the deeper scientists look into black holes, the stranger the universe becomes. Inside them, time appears to stop, space twists beyond recognition. Information may never truly disappear, and reality itself might not be fundamental at all. Some physicists now suspect that space-time could emerge from something deeper, a hidden quantum structure beneath the universe we experience every day. And if that's true, then black holes are not cosmic dead ends. They are doorways. Tonight, we're diving into the final mystery of black holes, from their origins in the 1700s to Hawking radiation, quantum paradoxes, holographic universes, and the shocking possibility that space and time themselves may be illusions. Because understanding black holes may ultimately reveal how the universe began. Long before telescopes could photograph galaxies, before Einstein reshaped physics, and before anyone even understood what stars truly were, to thinkers in the late 18th century imagined something extraordinary. An English clergyman named John Michell and a French mathematician named Pierre-Simon Laplace both arrived at the same disturbing idea. Independently, what if a star became so massive that not even light could escape its gravity? At the time, physicists already understood the concept of escape velocity, the speed required to break free from an object's gravitational pull. For Earth, that speed is about 11 kilometers per second. For the Sun, it's dramatically higher. But Mitchell and Laplace asked a terrifying question. What happens if gravity becomes so strong that the escape velocity exceeds the speed of light itself? The answer was astonishing. Such an object would become invisible, a dark star. Light emitted from its surface would simply fall back inward, unable to escape the object's immense gravity. This idea emerged more than a century before Einstein's theory of relativity. And yet, somehow, these early thinkers had already glimpsed the possibility of black holes. Laplace even wrote that the largest objects in the universe might remain unseen because of their magnitude, and eerie prediction mod in the 1700s. But there was a flaw in their understanding. They imagined gigantic stars becoming black holes purely through mass. What they didn't realize was that you could also create extreme gravity by compressing matter into a tiny region of space. And that realization would change physics forever. In 1915, Albert Einstein introduced general relativity, a revolutionary theory that replaced Newton's idea of gravity. Gravity was no longer a force pulling objects together. Instead, massive objects warp spacetime itself. Planets orbited stars because they followed curves in this distorted cosmic fabric. 1 year later, physicist Carl Schwarzschild discovered a mathematical solution to Einstein's equations. It described spacetime around a perfectly spherical mass. At first, it seemed like an abstract mathematical curiosity, but hidden inside Schwarzschild's equations was something extraordinary, a boundary beyond which escape became impossible. What we now call the event horizon. If an object collapsed within a certain radius, later known as the Schwarzschild radius, Gravity would become so intense that even light could never escape. For the Sun, this radius is only about 3 kilometers. Imagine compressing an entire star into a sphere smaller than a city. Do that, and the Sun would become a black hole. Schwarzschild himself didn't fully realize the implications of his equations, and for decades, many physicists believed black holes were mathematical fantasies rather than real objects. Even Einstein resisted the idea. The notion that nature could compress matter infinitely seemed absurd, but the mathematics refused to go away, and eventually, the universe itself would prove Einstein wrong. A star is essentially a balancing act. Gravity constantly tries to crush it inward. At the same time, nuclear fusion inside the core pushes outward for billions of years. These forces remain in equilibrium. But stars are not eternal. Eventually, they run out of fuel. Fusion slows, pressure drops, gravity wins. For smaller stars like our Sun, collapse eventually stops, leaving behind dense remnants such as white dwarfs. But for sufficiently massive stars, nothing can halt the collapse. In the late 1930s, physicist Robert Oppenheimer and his student Hartland Snyder showed that under the laws of relativity, massive stars could continue collapsing indefinitely. No known force could stop them. The result? A black hole. Matter collapses beyond the event horizon, trapping everything inside. Not even light can escape at first. Many physicists rejected the idea entirely. Arthur Eddington famously argued that nature would prevent such absurdities. But nature had other plans. Today, black holes are no longer theoretical. We have observed stars orbiting, invisible objects with enormous mass. We've detected gravitational waves from black hole collisions. And in 2019, humanity captured the first image of a black hole shadow, a glowing ring surrounding darkness itself. One of the most important scientific images ever created. Black holes are strange, not simply because they trap light. They challenge our understanding of time itself. Imagine watching an astronaut fall toward a black hole. According to Einstein's relativity, the astronaut's clock would appear to slow down from your perspective, slower and slower and slower as they approached the event horizon. Time would appear to freeze completely. The astronaut would seem suspended forever at the edge of the black hole. This confused physicists for decades. How could anything actually fall into a black hole if time stopped at the horizon? But relativity contains a profound truth. Time is not absolute. From the astronaut's perspective, nothing unusual happens at the horizon at all. Their clock continues ticking normally. They simply fall inward. For sufficiently large black holes, they might not even notice crossing the event horizon. No wall, no flash, no warning. Just silent descent into darkness. This is one of the strangest aspects of relativity. 2. Observers can experience time completely differently, and both are correct. Black holes expose this reality in the most extreme way imaginable. At the center of a black hole lies perhaps the greatest mystery in physics, the singularity. Asterisk. Popular culture often describes it as an infinitely dense point, but according to Einstein's equations, it may be something even stranger. Not a place in space, but the end of time itself, inside a black hole. Space-time becomes so distorted that the roles of space and time effectively switch. Moving toward the singularity becomes as unavoidable as moving toward tomorrow. You cannot stop. You cannot turn around. The singularity lies in your future, and according to relativity, tidal forces become infinitely strong. Objects are stretched and compressed violently, a process scientists call spaghettification. Atoms ripped apart, protons destroyed, matter erased, at least according to Einstein's theory. But most physicists believe relativity breaks down before reaching the singularity. Something deeper must take over. A quantum theory of gravity, and black holes may be the only places in nature where quantum mechanics and gravity collide directly. That's why physicists are obsessed with them, because somewhere inside black holes, the next revolution in physics may be hiding. In the 1970s, Stephen Hawking made a discovery that shocked the scientific world. Black holes are not completely black. Using quantum mechanics, Hawking showed that black holes slowly emit radiation, now known as Hawking radiation, over unimaginable timescales. Black holes evaporate. Eventually, they disappear entirely, and that created a terrifying problem. What happens to the information about everything that fell inside? According to quantum physics, information can never truly be destroyed. Burn a book, explode a planet, vaporize a star, in principle, the information still exists somewhere in the particles and radiation produced, but Hawking's calculations suggested black holes erase information permanently. That would violate one of the deepest laws in physics. This became known as the black hole information paradox, and it triggered decades of debate. Did black holes truly destroy information, or was our understanding of reality incomplete? Today, many physicists believe information is somehow preserved, encoded subtly in Hawking radiation itself. But exactly how this works remains one of the biggest unsolved mysteries in science, and solving it may reveal the true nature of space-time. One of the strangest discoveries in theoretical physics emerged from black hole research. The amount of information a black hole can contain appears proportional not to its volume, but to the surface area of its event horizon. That sounds impossible in normal life. Storage depends on volume. A larger room holds more books than a smaller one. But black holes behave differently. This led physicists toward an astonishing idea. The universe itself may work like a hologram. Everything happening inside a region of space could potentially be described by information encoded on its boundary. A lower dimensional reality generating the higher dimensional world we experience. This concept became known as the holographic principle, and surprisingly, certain mathematical models suggest it might actually be true. If so, space and time themselves may not be fundamental. They may emerge from deeper quantum processes, especially quantum entanglement. In other words, reality might be built from information, not matter, not energy, information. It's one of the most radical ideas ever proposed in physics, and black holes forced scientists to consider it seriously. The deeper researchers study black holes, the more connections they discover with quantum computing. This is where modern physics becomes almost surreal. Quantum computers store information using qubits, fragile quantum states easily disrupted by the environment. To protect information, scientists use sophisticated error correction systems and, astonishingly, the mathematics describing quantum error correction appears deeply connected to the mathematics of space-time itself. Some physicists now suspect that space-time emerges from networks of quantum entanglement, like an enormous cosmic information system. Geometry, perhaps. Even gravity itself could emerge from quantum relationships. Beneath reality, it sounds almost science fiction. But this is serious frontier physics asterisk. Black holes are no longer simply astronomical objects. They are laboratories for understanding existence itself. The universe may be far stranger than humanity ever imagined. At the center of nearly every galaxy lies a supermassive black hole, including our own Milky Way, Sagittarius. It contains roughly 4 million times the mass of the Sun. The black hole in galaxy M87 is even more extreme, over 6 billion solar masses, and we now possess images of both these. Cosmic giants may play critical roles in galaxy formation itself, yet scientists still don't fully understand how they formed. The James Webb Space Telescope is currently searching for answers by observing the earliest galaxies in the universe at the same time. Gravitational wave observatories like LIGO are detecting black hole collisions across the cosmos. Ripples in space-time itself, we are literally listening to black holes merge. And every new observation reveals more mysteries. The universe is filled with billions upon billions of black holes, not rare anomalies, but fundamental cosmic structures. Perhaps the most profound possibility is this: understanding black holes may help us understand the Big Bang itself, because black holes contain singularities, regions where space-time breaks down, and the Big Bang may represent another singularity, the beginning of time. To understand the origin of the universe, we may first need to understand the end of space-time inside black holes. That's why physicists believe black holes could ultimately lead to a complete theory of quantum gravity, a theory capable of explaining the birth of the universe, the nature of time, the structure of reality, and perhaps even why anything exists at all. Black holes are no longer just astrophysical curiosities. They are keys, possibly the keys to the deepest hidden architecture of existence. For centuries, humanity looked at the night sky and saw darkness. Now we know that inside that darkness are objects so powerful they bend time, trap light, and challenge the foundations of physics itself. Black holes were once considered impossible. Today, they may hold the answers to the biggest questions humanity has ever asked. What is space-time? Can information ever truly disappear? Did the universe have a beginning? And what hidden reality exists beneath the world we experience every day? The closer we get to understanding black holes, the closer we may come to understanding reality itself. And perhaps that is the greatest mystery of all. If you enjoyed this journey into the universe, subscribe for more deep explorations into black holes, quantum physics, cosmic mysteries, and the hidden structure of reality. Because out there in the darkness, the universe still has secrets left to reveal.